Today's video is about the water ionization constant. Even highly purified water has a slight conductivity that is only observable if measurements are made with very sensitive instruments. According to Arrhenius's theory, conductivity is due to the presence of ions. If the water is purified, what are the ions that are present? It turns out that water will ionize a very small amount. This means that at any given time, water will have some hydronium ions and some hydroxide ions present. Just as with any chemical reaction, an equilibrium constant can be calculated for water. The value is very small, which means that the reactants are favored in the reaction. In fact, 2 of every billion molecules in pure water exist in ionized form. The ionization constant of water is a very important value in acid-base chemistry. The symbol K is still used, but with a subscript of W for water. The ionization constant for water is equal to the concentration of hydronium ions multiplied by the concentration of hydroxide ions. This value is always equal to 1 times 10 to the negative 14 at SATP. kW gives us a lot of useful information. For starters, it tells us that in pure water, the concentration of hydronium ions is equal to the concentration of hydroxide ions. This equality is also true in other neutral solutions. Because of this relationship, the concentration of hydronium and hydroxide ions can be determined by taking the square root of the ionization constant of water. Remember the modified Arrhenius theory from our last session? It told us that an acid will react with water to produce hydronium ions. When an acid is added to water, then the concentration of hydronium ions in the water will increase. This means that acidic solutions have a concentration that is greater than 10 to the negative 7 moles per liter. Any solution that has hydronium ion concentration that is less than 10 to the negative 7 moles per liter is basic. kW applies to pure water and any solution that is mostly water. This means that the ionization equilibrium will be involved in any reaction that is going on in aqueous solution if hydronium or hydroxide ions are involved in any way. We can use the water ionization constant to calculate the hydronium and hydroxide ion concentration if the other is known by rearranging the expression. In this example, the hydronium ion concentration of an industrial effluent is known. The expression can be used to calculate the concentration of hydroxide ions. This example has a few more steps. We are asked to find the hydroxide ion concentration of a solution that has been prepared from pure hydrogen chloride. The first step would be to use the mass and molar mass of HCl to determine the number of moles. This value would then need to be divided by the volume of water in liters. Once the concentration is calculated, then the expression for the ionization constant for water can be used to calculate the concentration of hydroxide ions. Please note that we can assume that hydrogen chloride is 100% ionized in water because it is a strong acid. Because it is ionized completely, the concentration of hydronium ions is the same as the concentration of HCl. Please review the equations for calculating pH and pOH. We will be using these logarithmic equations throughout the rest of this unit. The pH scale is related to the concentration of hydronium and hydroxide ions in a solution. Don't forget to be mindful of the special rule for significant digits of logarithms. Only the digits that follow the decimal point in pH or pOH are significant. Please complete the December 11th quiz.